Welcome to lecture number 3 for ECE 401 Senior Design 1. In this lecture, we're going to be looking at breadboards and a Raspberry Pi Pico, Zero. Now, in Senior Design 1, you can use a microcontroller if you want. You can choose not to use a microcontroller. It's totally your choice. Microcontrollers can simplify some designs. They provide a great deal of flexibility. They make changing your design as easy as downloading a program, but you don't have to use a microcontroller. For example, we got to the moon in the Apollo mission before microcontrollers. They're not absolutely necessary, but they are really useful tools. So if you do want to use a microcontroller, that helps lead into Senior Design 2 and 3. Many projects in Design 2 and 3 use microcontroller. Getting used to using one in 401 is not a bad idea. However, if you do choose to use a microcontroller, you're required to use a Raspberry Pi 2040-Zero. Now, that's the same processor we use in 476 Advanced Embedded Systems, so there's lots of help online on using this microprocessor. The one we're using has got a smaller footprint. For example, the microprocessor on the left, that's the Raspberry Pi Pico. The one we use in Senior Design is the RP2040-Zero. Same processor, same programming, just fewer I/O pins. In Senior Design, this has plenty of I/O pins, so we'll just be using the Raspberry Pi Pico Zero. They're also fairly cheap. They're $3 each, and we have a lot of them in stock. So in this lecture, we're going to be looking at two things. One is breadboarding. Do's and don'ts with breadboarding, what they are, how to use them. We'll also look at hardware, how to wire up a Raspberry Pi Zero, how to connect it to a push button for binary inputs, how to connect it to an LED, and in software, some basic programming on using Python on the Raspberry Pi Pico. Again, if you want to get more information for using a Raspberry Pi Pico in Python, that's the course, Advanced Embedded Systems. Just go to Bison Academy, 476, and it's got lectures, videos, sample code, more than you want, but it's available. It's a resource. So, going back to breadboards. Where you are currently in Senior Design, you should have your project picked, have a paper design. You can then test your paper design in Circuit Lab. Once that works, you want to build it on a breadboard. The reason for a breadboard is everything that works in theory doesn't always work in practice. You might need to adjust some resistors, try to get the currents closer to 20 milliamps, make some fine adjustments, and verify that your circuit is correct. That's what a breadboard's for. Breadboards are really easy to modify. You can take wires, pull them out, move them around, get the circuit to work. Once you get the circuit correct, then you're ready to transfer the schematics to a PCB and make it more permanent. Now, most of the breadboards used in ECE are 830 type breadboards. The ones in this class are the smaller, the little 400 pin breadboards. Look like this. The way they work is if you flip them over, peel off the back, which I don't recommend you do because it ruins the breadboard. But if you do peel off the back, you'll see these connectors. What that tells you is these wires are shorted left to right. These wires are shorted top down. So typically what you do is you make the outer rails your power. For example, I would usually make this plus 5 volts and this one ground. Likewise over here, plus 5 and ground. And ground and 5 volts are very commonly used, so you have access to those pins wherever you want. You take your IC then and stick them across the center divide. What that does is that gives you connections to each pin on your IC, and you connect your wires. For example, here's a breadboard with a 5-volt regulator. This pin right here, the top row is 5 volts. The second row is 0 volts, 5 volts and ground. Here's my ICs going across the center. These 4 pins, these are all connected to pin 4. 5, that's pin 5. These are all connected to pin 1 and so on. So I can then connect different devices to pin 1, different devices to pin 2, using resistors, capacitors, and so on. A couple things to note. On this board, I've color-coded it. Black is ground. Red, well, it should be red. I ran out of red wires, so I made yellow 5 volts. And white are your signals. That makes it a lot easier to tell, do you have ground power to your chips correctly? I can see where the connections are. I'm going to be talking about that today. A couple do's and don'ts on building breadboards. Now, the purpose for breadboard is to verify that your design works in practice. So the procedure is come up with the requirements, then do a paper design. That should work in theory. To check your paper design, simulate it. Put it into Circuit Lab and verify the transistors are saturating, currents are 20 milliamps, the diodes, stuff like that. Once the simulation works, put it on a breadboard. That verifies that what works in theory really does work in practice. It also lets you adjust, move the wires around, make sure you got the wiring correct, you got the base emitter collector correct on your transistors, and so on. Once the breadboard works, you're ready to transfer it to a printed circuit board, PCB. PCBs are more permanent and abuse tolerant, less sensitive to noise, smaller, easier to package. But the problem with the breadboard is if one of the wires is wrong, it's really hard to fix. You want to get the schematics right before you build the breadboard, before you build the PCB. And that's the purpose of the breadboard. Verify you got the schematics right. There's a couple tricks in breadboarding. First, keep your circuit neat. If you have a nice, clean, neat circuit, it's much easier figuring out what's going on. When it doesn't work, I can probe, see where the voltages are. If you have a rat's nest like the bottom circuit, it's really hard to debug, really hard to figure out why it doesn't work. Oftentimes, if you come up to me and say, my circuit doesn't work and it looks like this, I'll tell you, rip out the wires, rebuild it. Cut the wires short. Cut them to length, keep them short, keep them close to the board. That keeps noise down, that makes it easier to see, it's easier to debug the circuit, figure out where the wiring is. It saves you time. Second trick, color code your wires. Make black, ground, red, 5 volts, other colors your signals. We got lots of colored wires. Colored wires are cheap. Want colored wires, come see us, we got them. If you have just random coloring in here, again, good luck trying to figure out why your circuit doesn't work. Third trick. In your Circuit Lab simulation, you'll calculate values for your resistors. And if everything's right, those should be correct. In practice, capacitors have a 20% tolerance, resistors have a 5% tolerance. If I'm trying to design this to be 100 Hertz, and I build it, it's probably going to be off a little bit. I need to adjust it. One way to adjust it is make this a variable resistor. One way to build a variable resistor is a potentiometer. What a potentiometer is a resistor with a center tap. As I turn a knob, the center tap goes left and right. What that lets you do is if I need a voltage, I can adjust the voltage from 0 volts to 5 volts by turning the pot. If I want to have a resistor, I just take one end short of the center tap. That means if this is, say, a 200 ohm resistor, I can go anywhere between 0 and 200 ohms. As I turn this, lets me adjust the resistor. By adjusting the resistor, for example, with this circuit, I can change the on time, the off time. This is a 555 timer that outputs a square wave. I can adjust the high time and low time with the resistors. Tune them to get it to meet my requirements. However, resistors cost about 2 cents each. Potentiometers cost about $1.55. Don't go overboard. You're allowed to use 2 potentiometers in your 401 project. So use them judiciously. They are useful, but don't go completely overboard. They are a lot more expensive. For example, suppose I have a circuit like this. I want the light to turn on at 50 lux. As light changes, this resistor changes. As resistor changes, voltage changes. At 50 lux, this is going to be something. I can calculate what it should be, but due to manufacturing tolerances, it's going to be a little bit different for each light sensor that I use. If I use my voltage reference as a potentiometer, I can make this voltage anything I want between 0 volts and 5 volts, so that I can adjust it so that this turns on at 50 lux, or whatever I want. So that's one use of a potentiometer. Use it to adjust a voltage. Another trick with breadboarding: include test points. Now, when you test your breadboard, you want to make sure that your circuit is correct. Think about it. How do you test your breadboard? What signals do you look at? What should they look like? What procedure do you use to test your breadboard? When you build your PCB, you want to do the same thing. So again, note on the breadboard which voltages you're looking at. Make sure those voltages are available on your PCB. Then ideally what you'll do is, to verify your PCB works, I'll have a table. And the table will show, here's what I calculated, here's what I simulated, here's the breadboard, here's the PCB. All these voltages should be the same. They won't be exactly the same, but they should be close. If your circuit's working correctly, you should have similar numbers. If one of them is way out of whack, you know where to look to debug your circuit. For example, suppose I had this circuit. This is a circuit that turns on a light when the temperature goes above 30 degrees Celsius. What I have here is a voltage divider. This is my variable resistor, my temperature sensor. Here's a comparator. It's actually a Schmitt trigger that turns on and off at a certain voltage. Here's my transistor switch. Turns on the light, turns off the light. Now, a couple of voltages I'd want to know. To debug the circuit, I want to know, do I have 5 volts? Do I have ground? What's the voltage at the light sensor? What voltage am I comparing it to? What's the output of the Schmitt trigger? Is it 0 volts, 5 volts, switching at the correct voltage levels? I want to make sure the transistor is saturated. Is the collector 0.2 volts when saturated, 5 volts when turned off? And I want to know the current through the diode. To do that, I'll measure the voltage across the resistor. To do that, I need to know TP6. So these are the test points that I'd want to know. Those are what I would use to test and debug my circuit. Measure those on your breadboard. Make sure those test points are available on your printed circuit board, so that when I build the PCB, I can take those measurements and verify my circuit's working. The last thing to note about your breadboard: keep your breadboard. Once your breadboard's working, keep it. Don't tear it apart. For example, this is a breadboard I built earlier. I didn't tear it apart because it's a pain to rebuild. Also, when you build your PCB, I want to verify the circuit works. The breadboard acts as a nice reference. Presumably, your breadboard circuit works. If the PCB is not working, you can use it to find out what's different. Why is the PCB not working? What's different on the PCB versus the breadboard? What that means is you're going to need 2 parts, 2 of every part. That's okay. You're eventually going to have 2 PCBs anyway, 1 for each student in your group. Have one on the breadboard, build the PCB with 1 set of parts. Once that PCB works, cannibalize the breadboard and build a second PCB. Okay, that's the first part of today's lecture, using breadboards. The second part is using Raspberry Pi Zero. Now, the Pi Zero and Pi Pico are the same processor. They're both based on the RP2040. The only difference is that the Pi has 33 I/O pins. The Pi Zero has 26 I/O pins. And actually, for this class, we can't use the pins on the bottom because they don't fit on the breadboard. So when you solder pins onto it, for example here, I soldered pins onto the Pi Pico or Pi Zero. I just soldered the left side and the right side, left the back side over here unsoldered. That way I can plug it into my breadboard to power it up. Now, to power your Pi Zero, there are 2 ways. One, you can connect a USB cord. That'll power it. That's useful for debugging your circuit, getting it working. In your final design, you won't have a USB cord. It should be powered from a 9-volt battery directly. So in that case, I take the 9 volts, convert it to 5 volts, and the 5 volts feeds straight into the pin number 1 on the Pi Pico. Now this pin is kind of dual use. It's an input and an output. If I connect through the USB, like over here, connect that to the USB port, then pin 1 is output. And notice this is color-coded. That's my 5 volts out. I could also take out the USB port and connect 5 volts straight to this rail, and that would power it the other way. So 2 ways to power it. Pin 2 is ground. That's the ground on your circuit. Like here, pin 2 is ground. That's the circuit ground for everyone. Pin 3 is 3.3 volts out. If you need 3.3 volts, it's available. We don't use that in this class. Note that you have to have a common ground, so the Pico's ground has to match the ground on everyone else in the circuit. So here's the ground line. That's the ground for my switch, ground for my speaker, ground for the LED. You have to have a common ground. In terms of the I/O pins, there are 15 I/O pins available on the Pi Zero. Don't use these pins down here. The reason being is they don't work on a breadboard very well. If I connect these up, well, this one doesn't go anywhere, and these are shorted. So don't use these pins. On the final PCB, you could use them. We don't need them in this class, so just don't use them. The other I/O pins can either be binary, 0 volts, or 3.3 volts. This is a 3.3 volt processor. You also have 4 analog inputs if you want. So for example, if I want to turn on a light when the temperature goes below 30 degrees, or have a freezer alarm, or a light sensor, whatever, I can connect an analog voltage to these pins and see what it is. That'll read 0 to 65,000 as the voltage goes from 0 to 3.3 volts. In terms of binary pins, these could be either inputs or outputs. For binary, logic 0 is 0 to 0.8 volts. Logic 1 is 2 to 3.5 volts. You're not supposed to connect 5 volts to a Pi Zero. The data sheets will allow it to go up to 3.5 volts. It's supposed to be 3.3, but there's a top tolerance. 5 volts is way out of range. You could damage it. Turns out the 2040 is actually a really tough processor. If you look at some of the websites, the user groups, people connect the Pi Pico to 5 volts all the time, and it doesn't seem to hurt it. You're not supposed to do that, but it seems to work. If you do that with a Raspberry Pi, however, you fried your processor. And Pis are about 50 bucks, so you really don't want to buy a $50 processor. You're not supposed to connect 5 volts to Raspberry Pis. To give an example of using a Pi Zero, let's build the following circuit. I've got 2 push buttons that'll turn on a light, turn off a light, turn on a speaker, turn off a speaker. Now for inputs, 0 volts and 3.3 volts are logic 0, logic 1. On the output, I can either output 0 or 3.3 volts. A limitation on the Pi Zero is you can only output 12 milliamps. So I've got to limit the current. That's what these resistors are for. So the schematic for connecting a Pi Zero to push buttons and a speaker would be like this. I assume there's an internal pull-up resistor connecting this to 3.3 volts. That's internal to the Pi Zero. We'll talk about that later. All I need to do is connect this to a push button to ground, and if the push button's not pushed, I read 3.3 volts. If the button is pushed, I'm shorting to ground, I read 0 volts. So what that looks like is as follows. So here's the Pi Zero, here's 3.3 volts, or actually 5 volts, ground. Let's see, jumping to the other side as well. Here's my push button. with the push buttons. If you zoom in on them, they kind of look like this. The push buttons are set up so these two pins are shorted, these two pins are shorted. When I push the button, that connects the top side, left side to the right side. And you can kind of see that here. If I zoom in on that, let's see if I can zoom. Yeah, I can zoom, okay. Kind of see the push buttons. It's got the connectors on the side of the push button. This is the top side, these are shorted. This is the bottom side, those are shorted. When I push the button, top and bottom get shorted together. I also have a resistor going from general pin 6 or 26 to an LED to ground, and another resistor going to the speaker to ground. That's 267 ohms. Okay, that's the hardware side. In terms of software, I need to take my Pi Pico and come up with a programming language to download your program to get it to do what you want. Now the Pi Zero and Pi Pico can be programmed in assembly, C, Python. We're going to focus on Python. Python is very similar to MATLAB. If you use MATLAB, you should be familiar with Python. So here's what that looks like. If I go find my Python, here's my Thonny. First thing you have to do is go to the web, find Thonny, download it, install it. Once it's installed, here's what it looks like. So you normally start with a blank screen. Let's get this out of the way. And first time you connect it, I won't get this message. I have to install MicroPython before I can use it. So to install MicroPython, I go to the lower right corner, click on it, tell it I want to install MicroPython. It will then ask you what type of processor it is. We're using the Raspberry Pi Pico. That's the RP2040 without Wi-Fi. There's also the Pico 2 that's got more memory, the W, which has Bluetooth Wi-Fi. We're not using that. We're just using the bare bones Pi Pico, also the Pi Zero. Connect that up. That'll take about 2-3 minutes. Once that's installed, I can then run Python. If you look at the lower right hand corner, like here is Python running Thonny. Click on the lower right hand corner when you're plugged in. You should see a COM port. I'm connected to COM 6. If I disconnect it, it's over here. If I disconnect it, I get an error message. I'm no longer connected. Connected to my computer again. There's the Pico. At that point, if you hit stop, I have this command window. Python is very much like MATLAB. It's an interpretive language. I'm actually running on the microprocessor right now. I can say A equals 2, B equals 3, C is A plus B, C is 5. I can do addition. What is 2 plus 3? 3 plus 4 times 5. Get it knows order of operations. It's a calculator, very much like MATLAB. You can add variables. You can print them out. Python, like MATLAB, is case sensitive. If I say A equals 2 and lowercase a equals 3, A is 2, lowercase a is 3. In Thonny, there is a program window up here. So this is like MATLAB. You can sit there and run everything in the shell window. That's like the command window in MATLAB. Or I can run it in the shell window. So what this does, if we go up here, I can write my program. Let's first stop it. Say A equals 2, B equals 3, C is A plus B. I can now run it. That's what this arrow does. I ran it, and the answer is 5. What the shell window is nice, or program window is nice for, is I can sit there and then change it. Suppose I want to do instead of 2 plus 3, what is 7 plus 3? The answer is 10. So this is kind of where you can write your programs, debug them, run them, see if they work. You can do binary inputs and outputs in Python. Now Python's a little bit different than MATLAB. Functions are included by using the import command. For example, the I/O pins are specific to the processor. The library that it contains the code for accessing the I/O pins is in the machine library. So say import machine. At that point, all the subroutines in the machine library are available. The way Python works, if I want to call a subroutine, like subroutine pin from library machine, I say I'm using library machine subroutine pin. The reason for that is if a different library also has a subroutine called pin, this avoids conflicts. This says use the pin subroutine from the library machine. Okay, so if I want to do inputs and outputs, the way you do that is if I want to have a variable called button, that's an output pin. I'll say that is defined using subroutine pin from library machine. I'm going to make that pin 0 in its output. When I have inputs, this says LED 0 is pin 6, it's an input. Pin 1, LED 1 is pin 7, input. LED 2 is pin 8, is an input. In addition, for input pins, I can just leave them floating, use an internal pull-up resistor or internal pull-down resistor. Now what the pull-up, pull-down resistors do is they set the default. If I leave the pin alone, it could be either high or low. That's up to the hardware to decide, is that 0 volts or 3.3 volts. If I do a pull-up resistor, what happens is if there's no connection, I read 5 volts. If I pull down resistor, if there's no connection, I read 0 volts. Now, in theory, to read a push button, I could either use a pull-up or pull-down resistor. With a pull-up resistor, what I want to do is take my push button, tie it to ground. That way when I push the button, it's grounded, button released, it's logic 1. I could use a pull-down resistor, in which case I have my push button, connect that to 3.3 volts. Normally use ground. The reason is because ground is ground, that's 0 volts, there's no confusion. On a pull-up resistor, I pull it high. Now is high is 3.3 volts or is it 5 volts? Depends upon the logic you're using. On Pi Pico, logic 1 is 3.3 volts. Again, you're not supposed to connect 5 volts to your Pi Pico. So I need to use 3.3 volts. That can cause problems. That will destroy processors occasionally when I get it wrong. So normally you don't do this. I use a pull-up resistor and connect the push buttons to ground. That's what's done here on the breadboard. So here's my push button. This pin is grounded. When I push the button, that pin right there is grounded. When I release it, it's floating. Due to the pull-up resistor, floating means logic 1. So here's an example of binary inputs. I'm going to use pin from library machine. I'm going to use library sleep milliseconds from library time. I'm going to define pin 14 and 8 to be input with pull-up resistors. Then here's my while loop. Forever and ever and ever, I'm going to be doing the following. I will read the value of button 0, read the value of button 1, print it. Wait half a second and repeat. So here's what that looks like. If I run it, then go over here and hit the first push button. When I press it at 0, release, press, release. The second button, push, 0, release, push, release. If I want to read a value of a pin, I use the subroutine value. So I say button.value, that's going to return either a 0 or a 1. Tell me what the value is of that pin. If I want to make an output pin, I can use the following commands. Toggle will toggle it, 0 goes to 1, 1 goes to 0. I can set it, clear it, make it low, make it high. So these are kind of redundant. Low and high are the same thing as value 1, value 0. Another useful routine is the time library. Now the previous program used that. In the time library, there's a bunch of different functions. We're using subroutine sleep. Now if I do the from machine import pin, that's kind of a shorthand. What that means is the subroutine pin comes from machine. I can just call it pin. I don't have to say machine.pin. Save some typing. I'm going to import subroutine sleep milliseconds from time. That's now available. And here's what that program does. I'm going to read the value of button 0, read the value of button 1, print them, wait a half a second, then repeat. And that again is the same subroutine that we had just a second ago. As I run it, there's button 0, button 1. And stop that program. What I can do with the time library? I can do things like let's blink an LED. To do that, here the LED is right here. That's connected to GP26 through a resistor. That then goes through the LED to ground. When this is logic 1, it turns on the LED. Logic 0 turns off the LED. The routine is going to initialize pin 26 to output, turn on the LED, wait for 2 seconds, turn off the LED, done. To see how that works, here's routine. When I run it, LED is on, LED is off. Try it again. LED turns on for 2 seconds, then turns off. There's LED down here. On, off. Python supports if statements, while loops, for loops. A for loop looks like this, like for I in the range of 0 to 6. This is a little bit different than MATLAB. In MATLAB, I would stop at 6. In Python, I stop at the number before 6, stop at 5. So for example, this is there's an indentation here. I'm going to have a for loop. This is nested for loops. This is actually over here. I'm going to count from 0 to 5. There's my first I. 0 to 5. There's the second I. Display the two together. That's a for loop. So example, here's a nested for loop. When I run it, I go through every combination. There's the D1 starts at 0 through 5. Then J goes 0 through 5, prints the sum. Now notice a couple things. In Python, this is a nested for loop. I have the first loop is executing, then the second loop. This spins around 5 times, 6 times. Every time I go through different index for I1. Indentation is important in Python. Indentation is how you tell what's part of each subroutine. So for example, if I pull this over here, what happens is this is now part of the first subroutine, or first loop, not part of the second loop. But run that code. Again, I spin through here 6 times, all I see is that result. At the end, J is equal to 5, and here's the results. If I pull it over, now I'm part of the second loop. And if I pull it all the way out, It just prints it when it's done. So in Python, Python's a little bit different than MATLAB. In MATLAB, you have end statements. In Python, you don't have end statements. You just have indentation. In MATLAB, indentation is decorative. In Python, indentation is very important. In fact, Python's going to bitch at you. If I do something like this, the indentation is wrong, and it's going to give me an error message saying, this is a for loop. I have to have something inside the for loop. If you want a for loop with nothing inside of it, here's command pass. That is just do nothing, a no op. And now it's not happy. Indentation is actually optional too. It could be 4 spaces, 8 spaces. As long as you're consistent, if I do something like this, I have inconsistent spacing, that gives me an error message. Python thinks this is another loop because it got indented more. Now it's part of the same loop. So in Python, indentation is important. That's a for loop. There are while loops. There are if statements. For example, let's turn on a light and turn off a light. So in this case, I'm going to have button 0 being pin 14, button 1 being pin 8, LEDs pin 26. I'm going to read the value of the push buttons. If the first push button is pushed, I'll turn on the light. If the second one is pushed, turn off the light. Display it, wait 100 milliseconds, then repeat. So here's what that looks like. So here's the program. As I run it, here's the value of the first push button, second push button, LED value. If we hit the first one, that's my set. Notice the LED turned on, value 0. When I release it, it stays on. What happens is the first button's not pushed, second one's not pushed. If the LED value doesn't change, if it was on, it stays on. This one is off. Now, if I push them both, what happens is the first one's pushed, turn on the LED. Second one's pushed, turn off the LED. It's actually flickering. You probably can't see it because it turns on, then immediately turns off. And then we have your on, off, on, off. And it's not always responsive. Again, there's a 100 millisecond wait routine. If I tap it, right there, it missed it. I tap and release during that wait routine. If I made this smaller, it's more responsive. As long as I hold the button down for 10 milliseconds, it's on-off. But disadvantage is I get this print printing out a lot of data. That would be an if statement. I can output tunes. So to output a square wave, I use the command PWM from the library machine. I'll again use the push buttons as inputs, LEDs and output. I'll add another output. Here's the speaker. Speaker's connected to pin number 6. I'll make that a PWM signal. I'll set the frequency to 220 Hertz and the duty cycle 0%. What I'll then do is, if I hit button 0, the speaker plays at 220. The duty cycle goes between 0 and 100% duty cycle. FFFF is 100%, 0 is 0%. Right in the middle, 8000 is 50% duty cycle. So that's the 50% duty cycle at 220 Hertz. Otherwise, it's 260 Hertz, 50%. If no buttons are pushed, make the duty cycle 0, 0% on, turns off. So here's what that looks like. I'll run the program. Nothing's printing out, so I can't see anything in the window here. But I can hear it. Here's I might be able to hear that. I have a 2-key piano. If you want to make it louder, you need to use a transistor. That's a future lecture. But for now, using a resistor right here, a 270 ohm resistor limits the current to 12 milliamps. 12 milliamps works. It's just really, really quiet. For loops, as mentioned before, for loops are similar to MATLAB. I have the range function. This goes from 0 to 4, a little bit different than MATLAB. When I do 0, 5, it stops at 4. I can do 0 to 5 steps of 2, or just do the numbers 1, 3, 5, 7. Again, the indentation tells you what's part of that for loop. If I want to count button pushes, I can do the following. So what this does, as I push a button, it starts out at 5 volts, or 3.3 volts, goes low. So no button push is 3.3 volts. It's got a pull-up resistor. Button push is 0 volts. What I'm going to do is wait. If the button value is 0, I keep waiting until I release it. Once I release it, I get to logic 1. Then when I push the button, it goes low. So this is the button push. That's actually falling edge. I will then increment a count, print n, and then wait. While it's low, I wait to release the button, push it, wait till release, wait to push. That's my falling edge. If I do that, I've got a counter. So here's what that looks like. If I run this program, when I press, release, press, release, press, release, press, release. I got a double count occasionally. That's bouncing. Some ways to eliminate bouncing. We won't get into that in this lecture. But I've got a counter. In Python, you can also use subroutines. Now in MATLAB, a subroutine is called a function. In Python, it's called a definition. The simplest subroutine just prints out a hello. It doesn't receive anything, isn't pass anything, doesn't return anything, just does something like in this case hello. Every time I call the subroutine hello, it screens as hello. I can also do that from the shell window. If I type in hello, it knows what that subroutine is at this point. If I type in say hello, it'll say hello. You can pass parameters to a subroutine. So here's the subroutine. I pass 2 parameters. I will take the first parameter times the second parameter, assign it to C, then print A, B, and C. If I say what is multiply 4, 6, I get 24. If I change that to 8, 7, I get 56. I can return numbers from subroutines. To return an operation, I have the return command. So here I'm going to have 2 numbers. I'll calculate the addition, subtraction, product, ratio, return those 4 values. So if I do, let's do the operations of 8 and 7. I will return, in this case, a matrix, an array containing 4 numbers. I can also return 4 individual parameters. If I call it this way, I'll return A, B, C, and D. So those are all different programs you can run from Python. Here's the 5th one. The 5th one uses the onboard LED on the Pi Pico. Now this is a Piranha, or this is a NeoPixel. To call that, I actually have to send a 24-bit stream connected to pin 16. The NeoPixel is connected to GP16. To do that, you can use this command bitstream. Now the timing of the NeoPixels is critical. Logic 0 is high for 300 milliseconds. Logic 1 is high for 700 milliseconds. What bitstream does is it lets you send data using precise timing. So to talk to the NeoPixel, I have to set up the timing. Logic 0 is high for 300 milliseconds, low for 900. Logic 1 is high for 700, low for 500. The NeoPixel is connected to pin 16, and let's just define 3 colors, red, green, blue. Those are byte arrays. The order is green, red, blue. These numbers are 0 to 255. If I have the wait loop, the main routine just keeps on repeating, displays red for 1 second, green for 1 second, blue for 1 second. What you'll get is the NeoPixel turning on red, green, blue. So to see that, here's the routine. If I then run it, you see the NeoPixel is going blue, red, green, blue, red, green, blue. More details of that go to 476. Somewhere we talk about NeoPixels right here. Okay, last thing to cover is how do you get your code to run on PowerUp? So currently, if I disconnect power, connect it, nothing happens. Let's set it up so the NeoPixel flashes green, red, blue, and then stops. To do that, what I do is go over to Thani, make sure I'm connected, everything's fine. Take the routine that I want. In this case, here's the routine that I want to run on PowerUp. I'm just going to have it run one time, and if statement just runs once, then exits. And let's run for 0.2 seconds. So when I run it, here's what it does. Let's make that bigger so you can see it. Run the program. Blip, blip, blip. I can make that longer. This is 0.5 seconds, each color. Red, green, blue. And then let's turn it off. Okay. To get that run on PowerUp, I do File. Stop the program. File, Save As. Now instead of saving to this computer, save to the Pi Pico. If I save it as main.py, what happens is on power off, power on, that program runs. So you're going to disconnect power, connect power, that run the program main. Disconnect power, reconnect power. That's what you'll be doing on your Steam Design project. Once you get your code working, save it as main.py, and it will execute on PowerUp. So that's a little bit of background on breadboards and the Raspberry Pi Zero. If you want more information, please go to Advanced Embedded Systems on Bison Academy. There's also W3 Schools, MicroPython. Fredscape is a pretty good site. I'll give you pretty good examples of Python programming on a Raspberry Pi Pico. And with that, that's lecture 3 for ECE 401. That should be enough to get you started on your breadboards and optionally on a Pi Pico.